Oh, in the previous lesson, we have learned how to use direct method, how to by experiment to determine the standard enthalpy change of neutralization, and for combustion, we'll use our setup called calorimeter to do so. But the question is, can all the enthalpy change be measured by a calorimeter? And the answer is not. Let's think about one of the cases here. Current react with oxygen to form carbon monoxide. Why is this enthalpy change cannot be found by calorimeter? Well, think about the scenario. You really have a piece of graphite and then you burn it in oxygen. Then what's the expected product? What's the expected product would be CO2. It means that we cannot stop the reaction at the stage of carbon monoxide. And the idea is that for this reaction, if we want to measure the enthalpy change, there will be further reaction and make it impossible. So that we cannot directly measure the enthalpy change by using experiment for this reaction. Well, then the second question is that, or say for example, the standard enthalpy change of maybe formation of CaCO3 cannot be measured by calorimeter. Why? And if you have no idea, then you write down the formula first. For forming 1 mole of calcium carbonate solid, then we need 1 calcium metal and then 1 carbon in forms of graphite is center state, and then we need 3/2 oxygen gas. Why can't this enthalpy change measured by a calorimeter? Think about it. If you really have a container and then you have some calcium metal, some graphite inside, and then also with some oxygen on the top, then you allow them to react, what will happen? They won't react under standard condition, or if they really react, then the probable product will be CaO and also CO2 instead of this CaCO3. Can you see the idea? So the answer for that, why we cannot measure the standard enthalpy change of formation of calcium carbonate, is that this substance, they will not react under standard condition to form CaCO3. So in these two scenarios, one of it has further reaction, and the other is that the reactant, they cannot react to form the designated product. Then the enthalpy change cannot be measured directly, cannot be measured by experiment. So that we use another method to do so, and we call it Hess's law. And Hess's law, the meaning of it is that the enthalpy change of a reaction depends on the initial state and the final state of the reaction only, but independent of the route it may occur. Just like you are taking a lift, from the ground floor, and then you go up for 2 floors, and then you take the same elevator to decrease by 3 floors, so that now your final state is that you are 1 floor below the ground, or you may at the basement. Can you see the idea? Or you can go up for 4 floors, and then you go down for 5th floor, and then your new position will be still at the -1 floor, that is the basement. Can you see the idea? The route itself, it doesn't matter at all. The only thing matter is that your initial stage and the final stage of the reaction. And if we apply the same idea, if we draw out the enthalpy level diagram is quite easy for you to understand. Your original state or the reactant is here. We name it maybe as stage A, and then finally is stage B. Then you can have so many ways for you to go to stage B. You can maybe go step 1 to form C and D, and then another step to form D and E first, and then finally you will form the stage B. When you are considering the enthalpy change between A and B, these two states, of course, the gap in between is the delta H. Then it should be independent of the route you choose, and you can have another pathway for it. It may go to another more thermodynamically stable state, F and G, and then even more and more thermodynamically stable state, H and I, and then finally you go back to stage B. Difference between the most initial stage A and then the final stage B, the energy gap is still this value. So that the route in between, it doesn't matter. As long as it has the final stage and initial stage the same, then the enthalpy change will be also the same. And this is the first idea for Hess's law. And the second idea is that if you really want to calculate the enthalpy change in between, you can actually sum up the energy change in each of these processes, and then you will get the same result. And if you are studying physics, the concept is just very easy for you to understand. For different routes of the people travel is called the distance, and then for the enthalpy change between this stage A and B is just the displacement of the reaction. And you say, okay, about the basic principle for Hess's law. Or if you do not understand up to this moment, it doesn't matter. I will give you a try of a real example. Well, let's continue about the application of Hess's law. Just think about the formation of SO3 from S. Then we draw the enthalpy level diagram first. For the y-axis, it is enthalpy, and then for the x-axis is the reaction coordinate. And then study the reaction one by one. First of all, one sulfur is a wood run, and I randomly draw, okay, sulfur is an initial state, and then we have with 1.5 O2 directly, so that the reaction consists of 2 S solid and then 1.5 oxygen diatomic molecule, and then to form 1 sulfur trioxide. And here is the product stage. Or you better name the enthalpy change next to the arrow. It should be negative 441 kJ per mole. And this route 1. And then for route 2, there are 2 stages. This one of the sulfur, if we add with one of the oxygen first, and maybe I draw it somehow scale. And then if we add only with one oxygen, so that 0.5 O2 left behind, and then 1S we add with 1 O2 to form 1 SO2 gas. And then the enthalpy change in between is negative 297 kJ per mole. Is okay. Then it will undergo also the second stage by reacting this SO2 and the extra 0.5 O2 to form the final product, okay, SO3. And the corresponding enthalpy change, it is negative 144 kJ per mole. And can you tell me the relationship between these two enthalpy? Okay, it dropped one time and then it dropped also the second time by 297 and 144 respectively, so that the overall change in root 2 it should be the summation between these two numbers, which equals to negative 441 kilojoule per mole. And it's just the same as root 1, which we directly reacted all reactants to form the final product. Can you see the idea of the Hess's law? No matter how many steps in between, then if your initial stage that is in here, 1 sulfur and then 1.502, and then the final stage it is SO3, and if you obey this relationship, then the overall enthalpy change would be the same, no matter how many steps is in between. Or we can say that it is independent of the route in which the reaction proceeds. Oh, then the second idea, if you understand about this enthalpy level diagram, what if you just have two thermodynamic data? First of all, if these species react directly, it has negative 441 kilojoule per mole as the enthalpy change for the first thermochemical equation. And then the second data is that we know the enthalpy change when S react with 1O2 to form SO2 is 297 kilojoule per mole. Now can we find out the rest of the part, that is the enthalpy change of this? And maybe we draw the enthalpy level diagram again. Idea is like this. Okay, first of all, it is S solid and then 1.502 gas, and then it can become SO3 gas directly, and the enthalpy change it is negative 441 kilojoule. And then the second information is that it be with only one oxygen, and then 0.502 is left, and then the product is SO2 gas, and the corresponding enthalpy change is negative 297 kilojoule per mole. And in this question I asked you for determine the energy gap between SO2 we add with 0.502 to form SO3. There's the energy gap here. Are you able to find out these values? And of course the answer is yes. It's because you just need to compare the energy gap between this amount and then this negative 297, and the difference between these two numbers goes to the unknown. Can you see the whole idea? And because now we are applying that the Hess's law, so that you can say that by Hess's law, maybe we define the new term as delta H. We would like to find this number, delta H equals to the difference between these two numbers, that is and of course after you draw this enthalpy level diagram, you can see that the initial stage is higher than the final stage of it, so that there will be a negative number, and after calculation you can get back this 144 kilojoule per mole negative as the enthalpy change for this process. Can you see the idea? Or another approach is that you can separate the whole procedure into root 1 and root 2. The root 1 is that if we undergo direct reaction is root 1. And then the root 2 is that we're starting from the initial state and then we go up one time and to 1 sulfur and then 1.5 O2, and then will fall back to the final product SO3. Is it okay? And if it is the case, we just need to sum up the enthalpy change of each of these process, and then you can know the overall enthalpy change. Oh, for delta H is our root 1, and then for root 2, because we go up first to get back this S and then 1.5 O2, so that for the first reaction we do the reverse, we will do the backward reaction of the first reaction. So if we do the backward reaction, then the enthalpy change will be the opposite with an opposite side. Originally is 297, and if we undergo backward reaction, then we add a negative sign on it, and we sum the second stage, the enthalpy change of the second stage, because now it's just the photon with the same direction of the reaction, so that we just add it by 441 kilojoule per mole. So the answer you obtain is also negative 144 kilojoule per mole. And this is the idea for the enthalpy cycle or the Hess's law. Is it okay? Well, if you still have no idea, then try another examples. Be reminded that for drawing this enthalpy level diagram, draw it in scale, and you try it first how to make use of these two information to draw an enthalpy level diagram. Yeah, if no, then just draw each of the stage one by one. The first stage is this. N2 gas, we have O2 gas, and I assume that this enthalpy level is right here. And then for the first reaction, it will form 2 NO gas, and then it will have an increase in enthalpy. So the idea is like this: go up for 180, and then go to the stage of 2NO gas, and this is the first stage. Oh, and then it will need that 2NO, and then we have with 1O2, so that for the stage we just add back 1O2 because it's one of the 3 reactants, and in order to balance the equation, we also need 1 oxygen gas in the initial state. It's okay. And then for the second reaction, it will react these 2 species to form 2NO2 gas. And you better draw it according to the scale, and the enthalpy change in between is 112 kilojoule per mole. Then what we have to do, what we want to find out finally, is that N2 we have with 2 oxygen to form NO2 gas, so that if we check the root, then 1 N2 we want it to react with 2 oxygen diatomic molecule to form 2 NO2, then the enthalpy change will just equal to this green arrow. Is it okay? Then of course, according to the direction of the arrow, you can see that the enthalpy change should be a positive value by Hess's law. Delta H equal to positive, and then the magnitude of it is just the number difference between this 180 and 112. So the answer is positive 68 kilojoule per mole. Or can you see the idea of Hess's law? Or other way is that you can assume that the root 1, it should be the directly goes to the NO2 side, so that we said that is delta H. And then consider another root is that we can, starting from the initial stage, to form a unstable product first, and then we undergo the second stage of reaction, and then to fall back to this 2NO2 stage, so that we just sum up the enthalpy change of these two arrows because they are in the same direction in the information given, so that we just add them up. Plus 180 and then plus negative 112, so the final answer will also be positive 68 kJ per mole. And this is the idea of Hess's law. Is it okay? When you may ask, okay, each time if you want to calculate the enthalpy change in a particular process, then you want to draw the enthalpy level diagram on scale, is quite time consuming, so that sometimes we will draw a simple version of the enthalpy level diagram called enthalpy cycle, and we do not need to draw them on scale, just the directions matter. And if I use the above as an example, then the way is like this. The first step is that we write down all the information in terms of equations. Then we have it already. We have totally 3 equations needed, so that we write down them already. And then write down the target equation. Now we would like to find out the delta H for this process, N2 gas plus 2O2 gas to form 2NO2 gas, and we consider this delta H as the target enthalpy change we would like to find out. Is it okay? So that we write it first. And then the question is, how can we apply the information? And each of the time we apply the information, we use one of it. Say for example, if you want to use the first piece of information, then we just add an arrow. Okay, and 1 N2 gas will react with 1 O2 gas. It means that 1 O2 gas will remain unreacted, and then for the first 2, it will form 2 NO gas. And in this enthalpy cycle, next to the arrow, we should mark down the corresponding enthalpy change. And up to this stage, we said that okay, the first information, it has been used already. Oh, and then time to use the second information, and just the species here. Is it okay? Then it will form 2 NO2, so that we can draw a complete cycle for it, and the enthalpy change is negative 112 kJ per mole. And after this, we have the whole enthalpy cycle. And you can see that it is much easier because we do not need to draw it according to the scale. We do not need to know whether it is increase or decrease or not. It's a simple version. And how can we calculate the result? Again, by Hess's law. And the idea is that we should be able to separate it to root 1, and this is the direct reaction, root 1. And then the second root is that it will go from the N2 and then to O2, and then to this stage, or to NO gas with 1 oxygen diatomic molecule first, and then to our product side, and this root 2. And the idea of Hess's law is that we just need to sum up all the enthalpy change in the root, then we can get the total enthalpy change. So that in root 1, only one enthalpy data is involved, is delta H. And then for the second one, there will be 2 enthalpy change involved. This 180, and then plus the second one, negative 112 kJ. And then we can get the number 68 kJ per mole. Can you see the idea? I'll show you by one more example, and then I think you can handle the rest of things. To follow the steps for enthalpy change cycle, we have to represent all the data in form of equations. So you must be familiar with the definition first. For salinity of combustion, it means that we burn 1 mole of that particular substance in oxygen completely. So we have to keep this graphite, the coefficient of it equal to 1. And then we add with another reactant, oxygen, to form CO2 gas. And the enthalpy change is negative 394.0 kJ per mole. And then for the formation of water, it means that we would like to form 1 mole of water from its constituent elements under standard state. So we have to keep the coefficient before H2O equals to 1. And here is the first step. Convert all the data into equations. And then the second thing is that we need to write down our target equation here. We want to find out the formation of C2H5OH liquid. This is the one we want. And the formation means that 1 mole of this substance is formed, so we have to keep the number before it 1. Is okay. So we just according to the coefficient 1 of the C2H5OH to balance the equation. And here is our target enthalpy change we would like to find out. It's okay. And after writing down this target equation and all information in terms of equation, then we can apply the equation one by one. As you may see, if you want to use the first information, if you compare the species involved, C2H5OH release 3 oxygen diatomic molecule. So if we really want to use the first information, we have to add back these 3 oxygen in the equation. Is it okay? So we're starting from the right hand side of it. It will form 2 CO2 gas with 3 H2O liquid. Then write down the corresponding enthalpy change. And up to this moment, we can say that the first information has been used already. It's okay. And then if you want to use the second information, then you're according to this second equation. For forming 2 moles of CO2, it means that the 3 H2O, they haven't been reacted, so that we keep the status, just copy them in our writing. However, for forming these 2 CO2 gas, we need 2 graphite. With 2 O2 gas. Then in the process, because we undergo the second equation twice, so that the enthalpy change involved will also be twice. Then up to this stage, the second information is used already. Then if you compare the species between the initial point and then this stage, to 2 graphite, it undergoes no reaction. Then originally there are 3.5 O2, and then finally 2 is left. It means that in the process 1.5 O2 is used to react with these 3 H2 gas to form 3 water molecule. So we use the first information 3 times. And here is the corresponding enthalpy change for the first step. And then again by Hess's law, for which one the enthalpy change is just delta H. And then for the second route, there are totally 3 processes to form 3 waters. This is the first step, and then the second step is to form carbon dioxide, and then finally is the backward reaction of the combustion data of this C2H5OH. Is it okay? So the overall enthalpy change should be the sum of these 3 steps. For the first step, because the direction is just the same, so that we add negative 206 times 3. And then for the second step, they are also in the same direction, so we just add back the enthalpy change. The most difficult part is for the first step. For the given information, we want the C2H5OH react with 1 oxygen to form CO2 and H2O. And when we are applying, considering the second route, then we undergo the backward reaction of it, so that the corresponding enthalpy change will also be opposite. So finally, you will get this negative 275 kilojoule per mole as the answer. Oh, you may ask, is there only one way to draw the enthalpy change cycle? The answer is not. And previously I showed you is that I use the first information and then the second information and then the third information, and indeed you can use these pieces of information flexibly, and let me show you. We still have to follow our first 2 steps by writing the information in forms of equations and then writing down our target equation and before we start. And then the next question is that how can you use the information? Say for example, I cannot think of how the first information can be used. Then I can actually start from the second and the third equation. Say for example, if I use the second information first, that is for graphite react with oxygen, and the way can be like this. We reacting these 2 graphite, and then of course we need 2 oxygen here, and then because we are now doing the second equation twice, so that the corresponding product would be 2 CO2 gas, and then the enthalpy change should be the delta H of combustion of graphite and then multiplied by 2. And then for the rest of the species, that is here, the 3 H2 gas and also this 1.5 and 0.5 O2, they haven't been used. Can you see the idea? And then the next step is and then now I can see that I can use the third information, so that I use the third information. However, in the process for 3H2 to react, we need 1 more oxygen, so that we add 1 more oxygen. And then because we now forming 3H2O liquid, and then for the carbon dioxide, it does not involve in the reaction at all, so they directly copy it. And finally, it's about the enthalpy change in this process, and we undergo the formation of water 3 times, so that the enthalpy change will also be 3 times. Is it okay? And then if you now check the first information, C2H5OH on the product side of our target equation, and then to form 2 CO2, 3 H2O. So what we need is this 3 oxygen gas, and then the corresponding enthalpy change is negative 1371 kilojoule per mole. Is okay? Then after this, you can check if your information is correct by counting the number of oxygen added. To become 2 CO2 and 3 H2O totally on the right hand side, we add 3 oxygen, and also for the left hand side +2 and then +1 oxygen diatomic molecule, so that these species are all balanced. And now you still get the same enthalpy cycle as before. For the first route, it should be delta H only. And then for the second route, there are 3 steps, forming 2 carbon dioxide, and then forming 3 H2O, and then finally is the backward reaction of the combustion of ethanol. So when we are doing with the enthalpy change, we just plus this number and then plus the enthalpy change of the second step and then minus the enthalpy change of the third step. So you can still got the same result by Hess's law. The delta H equals to plus 394 times 2 and then plus negative 286 times 3 and then minus negative 1371, and you can still got the same result. And if you are very familiar with this step, we can actually make the cycle even more easy. But some people, they consider the enthalpy change, two pieces of information together, and the enthalpy cycle, it will look like this. For the first step, you can actually use the third and the second information together to form with 2 CO2 gas and then 3 H2O. And if you do the counting for CO2 to react, we need totally 2 O2, and then for H2O to react, we need totally 1.5 O2. So in total, we need 3.5 O2. However, in the system, there is only 0.5 O2 is given, so that the net supply of oxygen should be 3 oxygen. Okay, and then again we copy the information for CO2 to form from 2 graphite. Then we need 304 times 2, and here is the corresponding enthalpy change. And then for the formation of free water, the value is equal to the formation of water undergo 3 times, so that times 3. And then finally for the combustion, what we need is 3 oxygen, and then the enthalpy change is this value. And again, when you are considering the second route, you can see that for the first 2 steps, they are in the same direction with our route 2. However, for the third step, it is opposite in direction, so that we need to sum the first 2 enthalpy change and then minus the enthalpy change of the combustion data of C2H5OH, and this is the third way to do it.